This class, we're going to introduce about how we can do plots in MATLAB. Okay, so why do we need to create plots? I think we already showed this in our first class when we introduced Excel, right? So the plots are the most direct way to show the data or the correlation of the data, right? To analyze the data. So it is very essential in data analysis. So basically, the large data sets are usually difficult to interpret as tables or numbers, right? It's difficult to find, let's say, the maximum or minimum and where the maximum or minimum occur, although there are functions to do this calculation as we showed in our last class. But having the plots are the most direct way to demonstrate or to conduct data analysis. Engineers and scientists use graphical techniques to reduce large data sets to help gain insights, and with the graphical representation, insightful trends and possible errors are more easily to be identified. Okay, so let's just get started with the 2D plots. So this class, we're going to talk about 2D plots and spend some time on 3D plots. Okay, so most of the time, the plots we're dealing with are going to be 2D. So the most easy way or the easiest form of 2D plot is just XY plot, right? So here it gives you some scripts. If we want to plot or if we want to make a plot that's showing the basically two sets of data, and it has a relationship of y equals sx squared, right? So then we'll just use this script here where we have x equals 0 to 10, and then we know y equals x squared, and we know that it has to be an element by element calculation. That's why we use a dot here. And then to make the plot, we just do xy, plot xy, and then basically this is the plot that we generated. Okay. So you can also add a grid to the plot, right? So you just need to type in grid on, right? Now you have the grid. If you don't like the grid, then you just grid off, right? So you can get rid of them. And then you can also add a title to the plot and also add the label axis, right? So for example, here, if we want to have the x being with the label of x, you just do x label, right? X, right? Y label, Y. And in fact, you can choose any type of label that you want. For example, if you want X label to be, right, so days in work, right? Y label being, for example, salary. Right? Let's put a higher value. Let's say $1 million. Right? Everyone wants this job, right? But you can choose whatever label that you want. And you can also create a title. So for example, here you can do title, my dream job. Okay, so you can see these are the different components of the plot. So you can also add multiple curves on a figure, right? So for example, you just had this curve when it's increasing, and you could also have a curve that increase even faster. For example, here you can see that while we still have the same set of x, right? So x is still 1 to 10. You already defined y equals x squared. So now let's name it as still use y here, right? You can name it y2 or whatever name that you want to use for this new y value, right? So you can do y2, and then let's make an even better job, right? So x to the power of 3. So then you can do plot x, y, x, y2. Okay, just create a new plot. So then you can see that by plotting again, it actually removed or sort of replaced our original plot, right? Now it's still figure 1. And then to add the axis label and title back on, right? You can do this, right? X label, Y label, title, right? So then you have the issue, right? So we know that there's one job that we want, there's another job. So how do we differentiate them? in the plot. Okay, so well, there's another way to make the plot, right? So for example, you can plot everything together. What you could also do is you can plot x, y, and then do hold on, right? So by typing in hold on, it basically keep this panel here. So when you plot a new plot, basically, it's not going to replace this plot, but instead plot on this existing plot. Okay, so then you can do again, let's say, just copy everything here. All right, so you can put the X and Y labels on as well as the title, right? So after you plot this curve, so if you want to make a new curve, right, or if you want to create a new plot, you have to remember to type in hold off. So basically, it released the hold on this existing figure. So now you can create a new figure. Otherwise, whatever data you plot on that you want to plot will be plotted onto this figure here without creating a new plot. Okay, so you could also create multiple figures. For example, if you don't want these two lines to be on the same plot, you can do figure 1 and then plot x, y, right? And then do figure 2. Let's try to expedite this process. Now you have to figure 2, which is an empty panel. So you can just double click on the Y2, right? Now you can basically have two plots that has different values, right? I'm going to show you how to combine these two figures together later on. Basically, just show one figure and then have these two subplots. Right? It's going to use the subplot function. So you can also, well, maybe I forgot about this slide here, but earlier you remember we plotted the X and Y together, right? So you may want to differentiate these two plots. So what you can do, say first, let's still have all of our legends here. If you want to differentiate these two curves, you would do legend. Okay, legend by typing in the name of this first curve and the name of the second curve. So for example, job 1, job 2. Okay, so now you can see this legend here. Basically, this is how we create different components of a plot, right? So then the next step is, of course, you can also change the line style, the point style, and the color. So line style, point style, I think this is also called marker style, right? And the color. So you have a lot of control in MATLAB plotting. So for example, now let's use a different set of data. Well, we can still use this set of data, right? So let's still do X and Y. It's still in our memory here. So clean up the screen. So you can do X, Y. Let's say if you want to change the marker, if you want to add a marker, right? First, if you want to add a marker, so you would do this, right? So now instead of having a line connecting all of the data, now you have each marker at each point of X, right? Basically, it's showing you the X and Y data value that you already calculated, okay? So you may want to connect these lines, these dots, or these markers, right? So you would just put a dash here, which means it's a line, okay? So you can also try to use a different type of dash. For example, let's do dash dot, right? Instead of having a straight line or bold line here, we can change it to dot dash line or even dotted line. Maybe dotted line is not allowed. So, or dash dash, right? So there are different line styles, or I think there's another way actually to just use dotted line. If you just plot this, it's going to give you the dots. Right? Basically, the dot is here represents a marker instead of a dotted line here. You try something else. Okay, it doesn't work. So And you could also change the color of your plot. So remember, we have it over here. You can change it to red. So what you do is you just type in R here. Red, R stands for red. Then it's going to change to the color of red. So what if you want to make two plots? So if you want to make two plots, so again, right, X, Y, X, Y. So you can do all the edits you want over here. Okay, let's make the dream job 1 to be the red marker with circle, red and circle marker with double dash line, right? Dash line. And then the next one being black. So the black marker is actually typed in as K. Okay, so you can use for example, diamond, right? Diamond, D stands for diamond. And then you could use just bold line. Okay, so then these are the two lines that you can create with the plot function. So again, you can do legend. And the legend is also going to change accordingly because now you change that to the red circle dash line and the black diamond bold line. Okay. So this is, I mean, you can see that there are a lot of like degree of freedom, right? So basically you can try and then see how you can control the way you want to present your plot. So for example, the line here, you can choose different types, right? So solid line, right, as we have already typed in, is just a dash. Dotted line is actually column. So if you column, right, you can see that this is dotted line, and dash dot line, dashed line, right? The point sign, point type, or the marker type, you can do point, circle, X mark, plus, star, so many of them, right? Triangle left, triangle right, triangle right. So basically, by having all of these different types of markers, you could differentiate data when you try to crunch it, when you try to put too much of uh, information into this plot. Right? Of course, we don't want the information to be so much, right? If there are, let's say, for example, more than 4 or 5 plots, then it's better to create 4 or 5 curves in a plot. Then it's better to create a new figure, right? So that people are not confused by the different types of markers on your plot. You can also change the color of the line. So we tried red, right? We tried black, and you can do blue, green, cyan, magenta, yellow, and so on. But normally, well, you can find out later that the green and yellow actually do not show quite well on the plots. Okay, so let's try just yellow and green. All right, so if you see the plot that we create here, basically it's quite difficult to get differentiated between these two. So basically, in our plotting, we prefer to use a color that are more bold, that has better contrast. Okay, so basically, this is a way we can make the plots, right? Generally, if you want to make a dash, I mean the marker with a plot. If you want to create a plot with markers and lines, right? You can also create plots just with markers, right? So setting a marker type without specifying the line type will suppress the straight line drawn by the default between the points and the lines, or among the points, right? So basically, if you just type in O here, it won't show you any line. Okay. So if you recall, in our first class, when we were talking about plotting with Excel, we said that if it's a data that is collected from experiments, right, from our sample collection, then we actually prefer to make the plot that only contain the markers, right? So we do not necessarily want a line between these, because by having a line, it suggests that the data in between these markers are real. Okay, you could have a fitted line, right? You can have a trend line here, but by connecting these dots, it means that these data are real. So we actually prefer not to connect them. And of course, you could also see some plots that has both line, like showing everywhere. It means that it's already a known function, a known relationship, right, between the X and Y. So basically, by having the plot, different types of plot here, it can indicate certain correlations, is what I'm trying to say. Okay, so for example, for this plot here, you can see this curve here. It is indeed this case because you are showing a polynomial function. Right? If it's a polynomial function, then you could connect all of these lines. But if it's just a data that random data that you collect from an experimental process, then we want a plot that does not have a line connecting them. Okay, so you can also do the rescaling of the axis, right? So here you're having a new function or new set of data. So for example, x equals -3, 1 to 10. So you may notice the difference here that this x here doesn't have the bracket. So in MATLAB, it is okay. So if you remove the axis, it's still going to give you one row of numbers. So y here is x to the power 2 plus x. Okay, so then you can do plot x, y. Right, it's going to give you this plot here. So if you don't want, for example, here it says, if you don't like the fact that the curve touches the axis, you can change the scale as follows. Right, so basically, if you don't like, for example, here the line is touching the axis, right? It's touching the horizontal line, y equals 0. You may want it to be zoom out a little bit, right? So to have some space over here and also some space over here. So what do? We can just rescale our axis. So what that means is that right now it's showing you the y range from 0 to 120 and showing the x range from -4 to 10. So to zoom out, it means that we can just make a plot that has a wider x limit and y limit, right? So to change that, you can just type in x-axis, right? -5. Let's start from -5 to 12. We don't necessarily need a comma. And then the y-axis from 0, let's say -5 to 112. Okay, so now it's basically zoomed out, right? So you have rescaled the plot. So another way to do this is you can do them separately. For example, you care more about the y-axis, so you can just type in y-lim, which stands for y-limit, right? -4 to 112. And then you can also change separately x-lim, right? So -5 to 12. Okay, so it's different ways to show the or rescale the axis. So you can also add annotations with the figures. For example, this is not a legend, right? We're not talking about legend, but just adding some additional notes on our plots. So we can do this. Right, so let's just copy whatever we had earlier. We still have the x and y. Oh yeah, now the x is a different set of data. So let's still do that plot x, y, right? Plot x, y. And then if you want to just add text, do this outside here. If you want to add the text, then you can just do text and then specify the location. And then test. Okay, so it's basically add a text over here. Legend, we already talked about it, right? So you can basically, normally when we use legend, it is when there are multiple curves on our plot and then we want to differentiate them, right? So for example, here, just use line 1 and line 2. Just type in legend in front of it. So you can also type in special characters. For example, if you want to show the x-axis having a like a symbol of theta, right? So if you want to do theta, then you will type in x label. So to type in special symbols, you will put a sign here, right? It's sort of like a dash sign, right? So it is not the normal dash sign that we use when we type in the website address, right? It's sort of like the reversed dash sign or divider. So then if it's theta, then you do theta. And then it's going to print theta, right? So then another thing you may wonder is, what if I want theta and then want a p after that, right? I want another letter, right? So you can see, you can just type in like that, or if you want to really differentiate these two, you can put a big bracket over here. Okay, so big bracket will divide your symbol from your other letters. Okay, so for example, you want theta and then it's theta A, right? Then you have theta A here. You can also do subscript and superscript, right? So to do subscript, you just type in a lower dash, right? And then you will have A over there. To do superscript, you will put an upper triangle, right? It will be over there. And then, for example, if you want to have a subscript or superscript that has several letters, because now if you want to do the superscript of ABC, then you see that the BC are back into normal, right? Again, you can use the larger bracket to put them together. And then you see the ABC over there. You may want italic, right? So if it's italic, then you would do this. Type in the reverse divider and IT, okay? So you have italic over here. You may want italic only for A and not for BC. Okay, so we're getting more sophisticated. Okay, so the italic should be here. Okay, so you see A is italic, B and C are not italic. Okay, does that make sense? Right, so of course you can also type in some others, right? My symbol. Okay, so you can see how it works overall. These are the special parameters. There's theta, you can also do, let me show the plot. You can do delta, right? You can do, what else? Alpha, right? So there's a list of special symbols that you can check for the, to put into the plot. Okay, so let's see, we can quickly check online. Right? So MATLAB special characters. So basically you can have the Greek letters, right? So there's a table that you can refer to. So you can do superscript, subscript, bold font, so on and so forth. But then here, this is a list of Greek letters that you can type in, right? We just set theta, mu, so on and so forth. Right? There are many of them that you can try to include in your plot. So this is also, you can see that this axis title, you can also do the same, the axis label. You can also do the same for titles, right? So basically, whenever you encounter the scenario that you need to print out a string, you can use this method, okay? So the special characters, so just to recap on the 2D XY plot, right? So these are nomenclature that we already talked about. So this is a 2D plot. We said that there are data symbol or data marker, right? There's plot title, right? This is a line or a curve. This is legend, right? This is legend that provides you additional information about plot. You have the axis. So the title here for each of the axes is called axis label. So I think in MATLAB, this is called axis title. So here in MATLAB, it's axis label. That's what we typed in here. So there's also tick mark, right? So tick mark are basically these tiny ticks that will divide the axis to different ranges. Right? So these are the different tick mark and tick mark label, right? So these are the label, the numbers. So basically later on, you will probably get some practice about how to change all of these components. So you can do a lot of things with the MATLAB plot, and each of them is an element. For example, you want to have another axis on the right-hand side, or triple axis on the right-hand side, right? So how do we add those components inside? Okay, some exercise here. So in one figure, plot y equals x squared minus 2x plus 3, and y2 equals minus x to the power 3 plus 3x plus 1 over x, for x equals minus 10 to x equals 10, right? So make y1 a solid line with green diamond points and y2 a dashed line with cyan x marks. Add a legend with both curves listed in it. So we can do is x equals minus 10 to, let's just separate by 0.1, 10. So y1 equals x to the power 2. Again, remember there's a dot sign, okay? Plus 3. Okay, y2 equals minus x to the power of 3 plus 3 multiplied by x plus 1 over x. Okay, so here you might want to pay attention that the x here, it can take the value of 0. Okay, so let's just, okay, so we have to do dot, right? Element by element. So let's just take a look at what y looks like when y2 looks like when x equals 0. So you can see it's 800 something, and then suddenly it goes to, let's see. There's 1 over x, right? 1 over x basically happens at, well, for x equals 0, it happens at the grid 101. Let's check 101. Okay, so 101, you see that takes a value of infinity. So I don't know how it's going to, how the plot is going to look like, but let's do the plot. Okay, so you have x, y1, x, y2. Okay, so for y1, you want it to be a solid line with green diamond. So you will do green diamond, solid line, y2 being dashed line with cyan x marker with dashed line. Okay, so if we just put these two inside, right, this is how the curve looks like. Right, it's very crowded mainly because we use 0.1 as the gap, right, as a step. So we can also, let's just try typing everything. So instead of using 0.1, let's use 0.5, okay? And then make the plot again. Now the plot looks less crowded. Right? These are the values that we get from the plot. And then you can further do legend, for example. y1, y2. Okay, so this is where we make this plot. So in the second figure, plot y equals tangent x and y2 equals sine x squared from minus pi to 2 pi. Scale the axis appropriately and add a grid. So you can do x equals minus pi to, let's see, separate by 0.05 pi. Right, 2 pi. Okay, so y1 equals tangent x, y2 equals sine x to the power of 2. And we said that we have to put a dot here because it's an element by element calculation, right? So plot x, y1, x, y2. Okay, so this is how it looks like. So the reason why we have this super large value is mainly because tangent of pi over 2 is infinity, right? So we don't want to show any infinity value here. So we want to basically scale the y-axis a little bit better. Okay, and at the same time, we know that the sine has a maximum value of 1, right? So basically, we just need to scale it to be, for example, y-axis changing from minus 0.5 to positive 0.5. So we can do y lim minus 0.5 to positive 0.5. right? So this is how it looks like. So you have the sine value over here, right? The sine square value over here and the tangent value over here. And you can see the rapid change of the tangent value, mainly because it moves from positive infinity to minus infinity, right? So this is how the curve looks like. And if you want to avoid this strange vertical line here, what you can do is you can just change the marker, right? Instead of connecting them, you just plot the marker or plot the symbol. Okay. So in this way, you can see how the value changes overall. Okay, you can also add a grid. Right. So this exercise 2. So you can do some more. There's another example. So basically, it's a MATLAB function that has a y equals this value for x between 0 and 52, where y represents the height of a rocket after launch in miles, and x is the horizontal distance in miles, right? So basically, you're launching a rocket and then rise up, and then it goes this way, curve up, right? So you have the height or the altitude, and also you have the horizontal distance. So this is the plot that makes this calculation, and then if you type in all the code here, right, the scripts here, you're going to have this plot. Okay, so we consider this plot to be an acceptable plot because you have the labels for x-axis and y-axis. You have a nice title, and it's also properly scaled. Okay, so you can also do plotting and curve fitting in MATLAB. So basically help you visualize the trend by plotting large data sets of data from experiments or from computer calculations. Can help you interpret the data. There are numerous graphical tools available in MATLAB. And curve fitting is also a powerful tool to basically find a mathematical model that can approximate your set of data. So we talked about curve fitting earlier in Excel. So we're going to talk about that later in this class. Okay, so that's about curve fitting. So we mentioned that we could actually plot a lot of data in MATLAB, right? So here, what I'll try to do is I'll go to the example that we used in our first class, which is the oxygen deficit, right? So we can conduct monitoring for at various locations, right? So you have day 1, day 2, day 3, day 4, day 5, and then you have different measurement at different points, right? Remember, we created how many data points? I think we created 5, right? We created 5 data points. So basically, let's just copy the data here. So the data. Okay, so remember, each column is 1 point, sampling point. Each row is specifying for a day. So to make the plot, you can just do plot, right? So we need to also specify what it means by each row here, right? So we should define day equals 1, 1, 5, because there are 5 days. And also, since the data is arranged in the vertical direction for each day, let's also do transpose, right? So now if you want to plot the data, data, right? You now have a matrix of data, so then you can generate this plot. Okay, so we mentioned that we should be using markers instead of lines, right? It's going to give you this set of marker here. So you can see that basically it's quite crowded by having the data arranged in this way, right? So what we can do is we can basically make one plot that has, let's say, 3 points, another plot that has 2 points. Okay, so then this is where we can use the subplots, right? Of course, you can create 2 separate plots. So what it means is you can do data. So if you just want to plot the first 3 points measurement, right? So you can do column that represents all of the rows, and then 1, 2, 3. Remember, this is about the matrix manipulation, right? If you want to plot the first 3 columns, then you have this plot. So we can create a new figure, and then if you want to make the plot of the rest of the data points, then you will do basically 4 to 5, right? So these are the 2 plots. But you may also want to combine these 2 plots together. So what do? We can do subplot 2, 1, 1. Okay, so then you can see now that you have basically a new figure that has the top part being separated, right? Its top part being a blank space, and now you can make the plot of the first 3 days, and then you can do subplot 2, 1, 2, and then plot the other part. Okay, so now you may wonder, well, what does the 2, 1, 1 and 2, 1, 2 mean? Okay, so for 2, 1, it's for the first 2 values, it represents how many rows, right? This is how many rows, and this is how many columns. Okay, so we're specifying a subplot or a panel that has 2 subplots, right? It has 2 rows and 1 column. And the third value actually means basically the plot number, right? The first plot and the second plot. Okay, so for example, if you want to create a 2 by 2 plot, right? So right now we're having 2 by 1. If you want to create a 2 by 2 plot, you'll do subplot 2, 2, 1, right? So you see now it's created like this, and then you make the plot, right? And subplot 2, 2, 2, you can create another plot, subplot 2, 2, 3. Now you see on the bottom corner, bottom left, make a plot, and subplot 2, 2, 4. Okay, so this is, you can choose to plot whatever data that you want, right? And within each of the subplot, it's the same. You just, before you create the new subplot, you will type in the X label, Y label, legend, and so on. So this is an easier way to arrange, let's say, different plots into one figure. Okay, so it's easier to edit, because a lot of times you want to use the space of a figure more efficiently, right? So basically, the subplots divide the figure window into a grid of m rows and n columns. The variable p identifies the part of the window where the plot is located. Right, so it's 1, 2, 3, 4. Okay, so this is an example. This is trying to plot the sine x and cosine x, right? So you can do the practice here, 0.1 into 2 multiplied by pi. That's the plot 1, 2, 1, right? So we said the first value is the number of row, the second value is number of column, right? The third one is basically plot number 1, right? So it means that it's 2 columns, 1 row. Okay, plot. Okay, I typed the wrong thing. It should be subplot, right? And then plot x sine x. Okay, subplot 2, 1, 2 x cosine x. Okay, so this is plot. And then there's another practice. So the following script creates a specific figure. Actually, it's the other textbook that we talked about. So which shows a plot of the function of this thing and the plot function of this thing. So you see it's actually quite sophisticated. So this is the x, this is the y, and then you have another set of x and y. So if we just copy everything here into our MATLAB script, so this is what you can get from the script, right? So you have basically 1 row, 2 columns. It's an efficient way to show basically more data sets. If we want to do comparisons, right? It's easier to do comparison, for example, under one measurement condition and so on. So there are other utilities for 2D plots. We have mainly been showing XY plot. You can also do polar plot, logarithmic plot, bar plot, pie charts, and actually box chart or the box plot. This is another thing when we are trying to do statistical analysis. Maybe we'll talk about this later on in our or in later classes. So you can do polar plots, right? Polar plots, we know that it's just a function of theta and r, right? So for example, if you do theta equals 0, 0.1, 0.01, r equals sine theta. So you can do plot theta r, right? If you do plot theta r, then you just have the x-axis still, x and y-axis being the linear scale. But if you do polar theta r, you will get this plot. Okay, that's basically giving you the sine function in the polar coordinates. Okay, so you can also have a scenario where you want to plot the logarithmic plots, right? So basically, these logarithmic plots will make the x-axis or y-axis or both of the x and y-axis being in the log scale. So this is the other set of code. For example, you can have the x values, the y values, and then you do subplots, right? So you can change it to be the x-axis being the in the log scale or y-axis being in the log scale. So let's just quickly try plot x and y. Okay, so this is the x, and we also have the y. So you can try, let's say, semi-log x. So this is x-axis. You see now it's in the x scale. I also have you give you a warning because negative value you cannot calculate the log of a negative value. Okay, you can also do semi-log y, or if you want both x and y axis being in the log scale, then you do log x y. Okay, so this is how the plot looks like. I think the log plots are quite helpful when you're trying to do Fourier transform and those a little bit more sophisticated calculations. So the logarithmic plots, so it's important to remember the following information. So you cannot plot negative numbers on the log scale because the log of negative number is not defined as a real number. You cannot plot the number 0 on the log scale, right? So you must choose approximately small number when you're trying to make the plots. And another thing we need to pay attention is that basically, if you have the log plots, and then let's say, I don't know if we can show the marker here. Okay, I can show you the marker here. So basically, these are the real values. Okay, so these are not what you have here. What I mean is what you have here are the real values of y that's calculated or defined earlier by the functions. These are not the value that's after you take the log. So for example, if you have the y value 100.2 that's shown in here, although it's located at 10 to the second, right? So this is not, it doesn't mean that the actual y value is 10 to the power of 102, right? These are real values, okay, instead of the ones that are calculated by log. It's just a different way of showing you the axis. Okay, so you can also make bar plot. So here you can do x equal, for example, you have the range of student score, right? So it can be, let's just generate a set of random number, right? Say 101. Okay, so you can do bar x. So because it's random, right? It's not, let's say, it's not normal distribution. So you have a lot of random, sort of like noise, right? So you can also, this is generating the vertical bar plot. You can also do bar horizontal, generate the values in the horizontal direction. So you can also create pie charts, right? So if you create a pie chart, then you just do x. So this is how it looks like, right? So each value, so basically each value that you already generated is going to represent certain fraction. So the total is the entire pie, right? So you could have regular large value that's close to 1. You could also have very small value. So easier way to show this can be rand, let's say x equals, and 5. Okay, only 5 values. So for example, this is the let's say how large of a pie it's representing, right? The larger the value, the larger the fraction it takes from the pie, right? So now if you do pi x, right? So you can see that one number represents 40%. So it's a summation, right? So it's using this value and divide that by the summation. Okay. So I think we talked about box plots earlier. So for example, now if we have 2 sets of data, right? So x one, let's say we have a measurement of some noise, right, over the 12 month, right? And we want to show the box plot of each month, basically summarizing all the data and then see how they change over time. So what we can do is basically we can do just generate a random set of number, right? So there are 12 months. Let's say each month we have 12 data points. Okay. So then you can do box plot x. Okay. So this is going to be more statistical, right? So you have 12 months, and then each month you have a set of data, and then it's generating these boxes, and then the box have the meaning of so the horizontal line here represents the median value, right? So the upper and lower range represents the 75th percentile and 25 percentile. Okay, and then the bar here represents the I think it's the 1%, 99 percentile and the 1 percentile. Okay, so in this way you can show overall how certain parameters change as a function of the different parameters. They're showing you as a function of month. Of course, we're generating random numbers, right? If it's random number, you will expect that these numbers to be around 0.5. But if we're talking about, let's say, rainfall data, or if we're talking about temperature, then you would expect to see a different type of box. Okay. So for more information about these different plotting options, you can always refer to MATLAB. So you can also do curve fitting. Basically, it's a linear regression. I think we showed that in our first class when we were talking about the Excel too, right? So it calculates the square distance between the data points and the modeling data points, and then it prevents positive and negative errors from by canceling them, right? So you can have these 2 data sets, right? So for example, you can put them in and plot x, y. We'll do circles here, right? This is our data. And you may want to add a line, right? A trend line here to do the best fitting. So of course you can do that with your hand. You can connect these 2 points and then guess what it is, right? It can be like -3 plus 15, right? So then you could also use the MATLAB's curve fitting function with the polyfit. Okay, so for the polyfit, you can specify how many orders you want the fit to be. Okay, so it can be since this is first order polynomial equation fitting, so you can just do polyfit x, y, 1 first order. Okay, it's going to give you the value in front of the x and the value in front of or the constant value, right? So y, the linear fitting will be this function. Okay, and overall, if you calculate the error, it's also smaller compared to the error if you use the hand to do the curve fitting. Okay, so once you have the curve fitting, of course, now you can make the plots and then compare these 2 different fitting. And then another way you can another thing you can try basically after you get the polyfit, you can also plot the polynomial function by just using the parameters you got. Okay, so for example, we already have this plot, right? So you can do hold on and then do polyval. Okay, so polyval will use these two parameters that you want to create the function. So for example, we can do polyval here and then here. Okay. So let's see polyval. Okay, let's do this. Plot x polyval x. Okay, so basically it plots the function. So it's plotting the function of minus 2.9x plus 14.2857. Okay, so in addition to this plot. Of course, you can also do polyfit of multiple values, right? So you can do a second order polynomial fitting, right? So in that case, you can copy this term here, right? Just paste what's in there. And then you can see that this is second order polynomial fit. You can do third order, fourth order. Let's do fifth order. Okay. So, and then you have these values. Type in or just copy them inside. Okay, these two. So the higher the order you have, actually, the better the polynomial fit it will be. You can see that when it gets to fifth order, right? So it's already fitting all of the data really well. But we don't want to overfit our data, right? So basically, if it's a simple mechanism, you expect it to be first order or second order type of fitting, right? We don't need to use higher order of the fitting to get better match with our experimental results. Okay, so this is a polyval function. So basically here you have the polyfit, and then in plotting you can do the polyval. So this is another exercise. Use a subplot to create normal and polar plots of this function with the same figure window, right? Remember the polar plots, right? You can create it. The normal plots is just, you don't need to worry about the x-axis or y-axis, right? But polar plots, you will use a polar function, right? So here, due to the time limit, I will not go through this exercise in more details. So you can also do the polyfit to find a third degree polynomial, right? This is the function, the results, and then you can use the polynomial fit to get the to find the best fit curve and the data points, right? So to plot them in the same set of plots. So you can do the three-dimensional, right? So this is you can also, we have been talking about the 2D plots, right? So you can also do the 3D plots, right? So a lot of times it's not only one parameter, or it's not only two parameters in terms of their correlation. It could be three dimensions. So one example could be, for example, we're trying to plot the location of an aircraft, right? If it's trying to spiral up, or if you're trying to spiral down and want to plot its coordinates, right? Longitude, latitude, and altitude, then we have to encounter these 3D plots. So to create the 3D plot, you can just use the plot3 function, right? So you can basically have the whatever function you want, right? And then to basically to basically create this 3D plot. So one thing we can try is, and basically it's showing you the time, right? So what is the time of the, let's say, the aircraft? What is the let me see. Oh yeah, what is the x value? What is the y value? And then what is the time? right? What is the t that you want to put inside? Okay, so then you can create this plot that looks like this. Okay, or actually, this is a different set of function. Okay, there's a different set of let me see. Yeah, well, I think it's the same. So here you have time having the value of t, right? That's the z, and then you have x and y, right? This is the x, and this is the y, the cosine t. So you have the plot that looks like this. So this is the plot 3 that give you the line curve, right? It shows you the 3-dimensional plot. But some people may have a hard time to understand what the 3-dimensional plot looks like, right? Because there's always, it depends on your, I would say, the angle that you're looking at this plot, right? So you may not get the exact value because here you cannot get the exact z value that you want, right? Because it could be closer to you, it could be further far away from you. So we would still want to convert the 3D plot into a 2D plot. So then at this time, the third dimension is actually converted into color. Okay, so this is called the surface plot. So we can basically use this script. So it has a z value, and then if you want to create the surface plot, let's just copy everything here and then check our plot. Since we used hold on, let's first hold off. Okay, so you have the new plot, and then let's just copy everything here. Do here. You can see that this is the surface plot. You may also want to convert it into a contour plot, right? It's a flat plot. It's a 2D plot. So then you could use the function over here, right? It will tell you the color here will tell you what the value means. And then since it doesn't have a color legend, right? At least it should let you know what the color represents. So you can just add color axis or the color bar, right? The color bar here will tell you what the color means for each of the value. So this is using the contour plot. So you could also see people using this p-color plot, right? So the p-color plot, instead of showing you the line, right, it's going to basically show you sort of an interpolation of all of the data points, right? It will give you a color map or the heat map of all the values that you want. So again, you can add the color bar, and then it's going to give you the value for each of the points. So you see the difference between the contour plot and the p-color is a contour plot will only give you a few lines, right? The p-color will give you the entire map. So it's sort of like the space is entirely filled up by the lines that's generated by the contour plot. Okay. So there are a few other options for making these 3D plots, and you can feel free to generate all of these. For example, there's mesh plot that we generated earlier. There's mesh C. I think it also gives you the sort of the interpolation or let's say the view that's directly corresponding to each line, or sort of adding the contour of these this 3D plot. You could also have the mesh Z that's connecting all of the data points to the surface at the bottom, right? There's also a waterfall. Okay, the fourth plot is a waterfall. So there are some requirements, and also there are some hints for making the correct plots. So maybe I can just quickly go through these requirements due to the time limit, right? So this is the following list that contains all the essential features of any plot. For example, you must label the name of the quantity and also its units. Units are very important, whether it's imperial unit, right, showing you the feet, or the standard unit showing you the meter, right? So if 2 or more quantities of different units are plotted, then you need to label them and also to include them in the legend, right? So each axis should have regular spaced tick marks at convenient intervals, not too sparse, not too dense, right? If you have a figure that has the range of 0 to 100, you don't want 0 and 100 being the only tick marks, right? So for example, use 0.1, 0.2. Instead of using some random or some number that are difficult to interpret, like 0.13, 0.26, and so on. If you're plotting more than one curve or data set, label each on its plot or use legend. If you're preparing multiple plots of a similar type, if this axis cannot convey enough information, then use a title. If you're plotting measured data, right? So this is what we talked about in Excel or also earlier in this class. So if you're talking about measured data, then plot each data point with a symbol, right, with a marker. So use the same symbol for each point in the same data set. If there are many data points, then plot them using the dot symbol. So sometimes data symbols are connected by lines to help the viewer visualize data, especially if there are fewer data points. However, connecting data points, especially with a solid line, might be interpreted to imply knowledge of what happens, what occurs between the data points, right? So because you do not want to give the false impression that the measurement between the data points are the measured data. So therefore, you need to be careful to prevent such misinterpretation. If you're plotting points generated by evaluating a function instead of measured data, then do not use a symbol. You just use a line, right? Generate many data points and connect the points with solid lines. So you want to add a grid, or a lot of times, I think most of the plots do not have the grid, but if the grid is helpful for you to make the plots, then you can use a grid function and then use the axis function to properly scale your plot. Saving the figures. So if you want to save a figure, you can just go to this plot here and then click on the save, right? So it's going to give you a pop-up window, and then you can choose what type of plot you want to save as. So most of the time, people will create JPG plot, but then .fig plot is actually a MATLAB type of plot function that retains the original data from the plot. Okay, it's easier for you to edit plot later on if you save it as the .fig plot. You can export the plot by export it as PDF or even print the plot if you want. So hints for improving the plots. Okay, so we were talking about requirement. So for improving, so we should start scales from 0 whenever it's possible. Right? So this is our general impression that the plot start from 0. If it's close to 0, right, the starting point of x-axis, then just make it 0. Use sensible tick mark spacing. If the quantity are a month, then you should choose the space of 12 because 1/10 of a year is not a convention for division. The same for time, right? 24 hours a day. You don't want to show something like a marker of 2.4 hours, which is not convenient. Minimize the number of zeros in the data being plotted. What that means is, for example, if you have $1 million, right? So you don't want to show 60 after 1. You want to use the scientific way of showing the numbers, 10 to the power of 6. Or in your original data set, you just divide everything by 10 to the 6 and show that this is showing you the million, right? Determine the minimum and maximum data for each axis before plotting the data. So then you set the axis properly. So for example, if the axis range from 1.2 to 9.6, then you don't want the axis to just start from 1.2 to 1.6. Right? The better way is to just use is from 0 to 10. Okay, and this will also allow you to use a tick spacing of 1 or 2. More ways to improve the plots. Use a different line type for each curve when there are several being plotted, right? Be aware to use colors to distinguish plot if you're going to make black and white printouts. If you use black and white printouts, basically the blue color and black line or green line are going to look the same. Do not make many curves in one plot, particularly if they're close to each other, right? So in that situation, either use subplots or just create a new figure. So then use the same scale limits and tick spacing on each plot if you want to compare information, right? So if you want to compare, for example, the height of a girl and a boy, right? So you want to use the same axis limits, right? You don't want to be one being, let's say, 0 to 2 meters and the other being 0 to 200 meters, right? Then in that case, if you want to do the comparison, it's difficult to differentiate, okay? As a summary for this class, we talked about plotting in 2D, adding the grid title, label, text legend to the plot, use proper scaling of the axis and the plot, plotting multiple curves on a figure, adding legend, plotting using multiple figures, plotting complex arrays, and then changing the line style, color, and point style, or the marker style. So we used or tried subplots. We can also generate other types of 2D plots, right? Bar charts, pie charts, or box plots, curve fitting, right? Polyfit, polyval, 3D plots, right? It could be coming quite in handy in more of the technical or research related plots. And then we also went through the requirements and hints for making good plots. Okay, so that's it for this class. And let me know if you have any questions. See you next time.